All right, guys. New types of reaction. Are you excited? Get excited. Okay. So in the past, you have seen all the organic reaction that produce either ionic or radical intermediate. Give you some examples. So you have seen this before. And the first one, hydrohalogenation of an alkene, so nucleophilic attack, and you get the cation intermediate. Right. Next one, we have sodium borohydride attack a carbonyl carbon. You get the anionic intermediate, and the last one is radical. So most reaction involve just either cationic, anionic, or radical intermediate. Now we're going to move on to a different type of reaction. We call this pericyclic reaction. Okay, so the intermediate does not involve positive charge or negative charge or even radical. Let's see what happened here. So you start with the 3 pi bonds and the intermediate from new sigma bonds and 1 more new pi bond. Neutral, okay, not cationic or anionic intermediate. Okay, and then you get a ring at the end called cyclic, so pericyclic. We also have an electrocyclic addition. Don't have to memorize all this. No, do not memorize this. We're gonna get into the detail and draw the mechanism. You don't have to memorize like 3 pi bond to 1 pi bond. So no, I never ask you that. As long as you can draw the mechanism, you're good. Okay. All right, one more. So electrocyclic addition start with 3 pi bonds, and you get 2 pi bond and 1 sigma bond at the end. Now these two, the driving force are the formation of sigma bond, and sigma bond are stronger than a pi bond, and that's drive the whole equilibrium forward. Okay. Last one, we have sigma-tropic rearrangement, 2 pi bond, 1 sigma bond, and you get new sigma bond and 2 pi bonds. You may ask like, hey, there's no driving force right here. You get the same type of bonds. Well, we'll see the detail later. Okay. All right, we're gonna start with the first one, cyclo addition. The first cyclo addition and the most common one we call 4+2 cyclo addition, or we call Diels-Alder reaction, and most people call this Diels-Alder. A little bit about the naming. So why do we call 4+2? Well, look at the starting materials though. We got diene, so 2 double bond. When we have 2 double bonds, how many pi electrons are there? Think 2 double bonds. So 1 double bond is 2 pi electrons. 2 double bonds, 4 pi electron. That's number 4. Okay, that's where the number 4 comes from. Dienophile. So dienophile got 1 double bond, right? So 2 pi electrons. So 4 pi plus 2 pi. That's where 4+2 come from. And we use the bracket as like in the nomenclature. Okay. All right, so this reaction consists of diene, so 2-ene, right? So we call diene or conjugated diene. We talked earlier, and we also have a dienophile. Now, enophile means love whom, love diene. Okay, like nucleophile, electrophile, similar to that. And dienophile usually contains an electron withdrawing group. We'll get there later. What electron withdrawing group is? All right, let's talk about mechanism real quick. Okay, so we have a diene react with a dienophile. When you draw the mechanism, this is going to happen. Take a look. We will take a double bond at the bottom. So take double bond and attack the bottom carbon of a dienophile. Okay. And we're going to use the double bond of the dienophile, attack the top carbon, the end carbon, the other go to the other end of the diene. So we draw from the middle, not from the top carbon, because the electron is right here, the pi electron. So we used to go from the middle, attack the end carbon. And this carbon is going to be over octet, so we have to move the double bond, push the double bond lower, 1 carbon down. Look like that. So the transition state look like a six-membered ring. So the red right here is a bond formation, okay? And right here also a bond formation right here on the left side, double bond. And the rest are breaking, and you get, here we go. All right. So basically we go from 3 pi bonds, okay, to form 2 new sigma bond and 1 pi bond. And the driving force is the formation of the 2 sigma bond. And sigma bond is stronger and more stable than a pi bond, and that's the driving force, drive equilibrium forward and release energy too, okay, because the product is more stable. Anyway, so this one way you can draw the mechanism in your textbook. If you use David Klein, David Klein does like this. So he drew 2 imaginary lines like that, because we are about to form this 2 sigma bond. So he drew the line like that. Okay, and instead of put double bond, attack the carbon, he draw from double bond, go to the line, and form the bond right there. Same thing on the dienophile right here on the right. Draw up to that imaginary line at the top. Okay, and lastly, this one the same thing. So push that double bond downward. There we go, same thing. All right. So 4+2 cyclo addition. So summarize real quick. So 4+2, the 4 come from 4 pi electrons from diene, 2 pi electrons from dienophile. All right. At the end, we are forming a cyclic compound. The cause of this reaction is 3 pi bonds, but what we got is 1 pi bond and 2 sigma bonds. So the starting material is more stable, and this reaction releases heat. Okay, so exothermic reaction. And here's how you draw the mechanism down here. Either one works. This is up to you. All right. So next one, we can look into the thermodynamic consideration. Why this reaction exothermic, and also why is it spontaneous or not. Okay. All right. Next video.